Thank you. All right, thanks so much for inviting me. This has been a lot of fun. So yeah, I'm going to be here for another couple of days as well, so I'm really enjoying myself. So I'll be happy to talk to more of you. Okay, so yeah, these are the people who I'm going to show their work. Most of them are grad students, and there's a few other faculty, and they've all done bits of this, and then hopefully I'll give them credit when I show you different things. Okay, so you had a talk about AI yesterday, right, in this very room, okay, and so there's some relationship between that and what I'm going to talk about today, and you know, there's some other things. So I do mostly the Lyman-alpha forest, intergalactic medium, but I use AI, and I'm sure everyone here uses AI. If I ask my students when I teach, how many of you do the homework with AI? They all put their hand up. They all use ChatGPT. They just use it to do their homework, right? And so they're all, even though they do that, they're all worried about what AI is going to do when they graduate, right? And so this is just some headlines from news articles in the last month, okay? And there's some, you know, local to my university, but you know, obviously you could find these kind of articles everywhere, right? What is the future of everything, right? And now we're all astronomers, so I'm like you, I'm most interested in what does AI mean for us, right? For our jobs, right? So for example, you know, are we going to have jobs? Is AI just going to do everything, right? And so you can see, obviously, the AI wasn't very good at doing this picture because the telescope is not pointing at the eye. So that already shows you that AI is not great, okay? But there are still some people who think that AI is going to take over our jobs, right? And so there are papers out there on arXiv about AI systems that can do everything, right? And so there was this one over the summer by Adam Moss, and there's one here by Paco Villascusa Navarro, right? Who, this was only a few days ago, a week ago, and they're both systems, multi-agent systems, which, and I'm going to talk about some multi-agent systems that I've worked on, but these are different ones. What they do is they're just a bunch of AI agents, a bunch of ChatGPTs, if you want, talking to each other, and they can generate full journal papers, right? They can actually, you know, go from and come up with an idea, supposedly, and then do analysis of data, write the paper, submit it if you want, right? And they're full papers. They look like real papers, and you can have a look at these papers. And so the question is, you know, what are we going to do? If this, you know, is the future of AI, you know, but I would like to argue that if you look at these papers, they look very convincing from a long distance, but if you read them, are they actually interesting? Was it done by somebody who was having fun and invested in their work like we are? I don't think so, right? And just, I mean, this is kind of silly, but you know, we have this term called AI slop, right? So if you look at the internet, it's full of stuff generated by AI. And I just wanted to make an example of how easy it is to generate, you know, journal papers or AI slop, right? So here I just put in, you know, a prompt, give me a hip hop song about this. And I apologize, I'm going to have to play at least the first bit till I get to the chorus because it says something in Chinese, which I've been told is not rude. But anyway, so we'll see. And you'll see that, you know, it sounds kind of human, but it is slop, right? So you can obviously give it any subject you want. So yeah, I'm not going to dance, but okay, you could dance if you want. Okay, so this is what it thinks I'm going to talk about. And then, you know, obviously I can make it sing in Chinese, but I don't know what it's saying, right? So okay. So, you know, this is what we call slop, right? That's the English word. I don't know in Chinese what the word is, but it's just something, you know, that the AI can do. It mimics a human, but it's not invested in it. It's not fun, right? Obviously, you can play around with this, but okay. I would have said that it's terrible, but apparently I looked in the news, and the #1 song on the US Billboard country charts is actually AI generated, okay? So I think that just shows that country music in the US is also terrible, is also slop, right? But okay, so anyway, so that's AI slop, right? And so, you know, sorry, please stop, okay. So you might have noticed that because of this, last week arXiv changed their rules, right? They don't accept in CS, right, and maybe it will come to astrophysics as well, AI-generated papers, okay? Because there were just too many. People would say, okay, write a paper about something and submit it, and, you know. And so they just said, okay, we need human peer review to be able to submit to archive, right? And so this is a new rule for CS, but it's going to happen probably in astrophysics, right? So I'm going to argue that, you know, the role of AI in astronomy is not to try and do this, although, you know, it's fun to try. You know, it's probably fun to build killer robots that will take over the Earth, right? But that's not a good thing, right? This is similar, okay? And so instead, I'm going to talk about AI that will help astronomers doing the boring things. You know, we do astronomy because we like to think about the universe, come up with ideas, not because we like to install libraries, right? I don't know, maybe some people like to install libraries, I don't know. Not me, but okay. And also, you know, calculations, they can be sped up. You know, obviously there are a lot of things you can do with AI that are not things you could do with traditional computing, and, you know, inference and other things, but also just I do simulations, so I'll talk about simulations, okay? Okay, so for example, why do we need AI to speed up calculations? And as you probably know, right, in this institute, any simulation you do, computational fluid dynamics, n-body or whatever, they're very expensive, okay? And so I'll show a bit. Our group's recent simulation called ASTRID, it used 500 million core hours, okay, to run to redshift 0. And supposing we want to use them to make mocks, huge surveys, so run many simulations, right? We obviously can't run many things that run, this one ran for 4 years, right? We can't do that, okay? We need to do it faster. Or if you want to do simulation-based inference, you know, you need many, many simulations. You should be able to run them very quickly. You know, we need some other way to do it, right? So I'm going to talk about how we can use AI to do that, right? And so we're always coming up against the fact that in cosmology we need a huge volume, we always need statistical significance, we actually need to beat down cosmic variance, okay, but we need lots of particles, right? We need high mass resolution, we want to make a dwarf galaxy or something like that, right? Or even smaller, hopefully, right? So we're always fighting these things, okay, and any innovation in simulations is to beat down that problem. And so in our group, we developed this AI super resolution technique, and what it does is it's basically a hybrid calculation between a neural network and a physics code, right? So you might say what we're going to do is we're going to super resolve a low resolution simulation and put in all the structure, okay, on small scales with AI, right? And so on large scales, we've got the n-body code and also now computational fluid dynamics, hydrodynamics, right, which we've done relatively recently, and that's running on a CPU. And then on the GPU, we've got a neural network which does some not very cutting edge CS stuff, but it's fine, a GAN and a UNet, and that puts in the small scales, and it puts in the small scale structure, right? And so that's what we're going to talk about. And that, in order for this to make any sense, you don't want to spend all your time here and 1% here, or you know, the other way around. You want to spend roughly equal time on both, okay, just to make it worth doing, okay? And so that's what we're sort of aiming to do, okay. Okay, so how does this super resolution work? And so here, this is just for the n-body code, dark matter only. I'll talk about the hydro in a second, but the idea is that you need to train it, and it's a conditional GAN. What does that mean? It has an input which is not just random noise, okay? It has a low resolution simulation input, okay? And so the GAN has an input random noise field, in this case, and a low resolution simulation, and then you train it and you compare it to a high resolution simulation, right? And you see, this is the high resolution simulation, and this is the generated one, where obviously the low resolution is what gives you the small scales, okay? And then you train that, and then eventually, hopefully, your generator can produce something which is like the high-res simulation, okay? Turns out that, you know, statistically that's fine, right? Because we're inputting random noise, and you probably know, you know, you can generate images, you know. Okay, for example, if you ask ChatGPT or something, it will use, okay, as a transformer, but it's similar, you know, it can generate images with an input of random noise. They're always different every time you ask the same thing, right? Here we can do that, but in simulations we don't necessarily want that. What we want is we want to be able to input the high resolution initial conditions and then run the generator so that it actually produces the output that it would have produced if it ran a full high resolution simulation, right? And so that's what we added to it. We put an additional unit which takes the super resolution simulation generated with random noise, and then it compares to a target simulation, and then basically it trains this unit to move the randomly generated small scale structure into the correct place, okay? And so what's the difference between the super resolution generator and the emulator? Okay, so the generator can produce a field, in this case a cosmological density field, that is statistically the same as the true field. So for example, if this was the generator, you have low resolution simulation, random noise, generator comes out and you get an example, a super resolution example. Put in different noise, you get a different super resolution example. But if you plot the power spectra, right, statistics, if the box is big enough, then they will be very similar, right? But if you plot the correlation coefficient of the individual Fourier modes between this was the true high resolution and the super resolution, right? They will be the same on on large scales, right here, because the input low res is the same as the true one, okay? So on these large scales, we have a perfect correlation of the individual Fourier modes, but then on small scales, because there's random noise that came in, even though statistically the fluctuations are the same as the true fields, on small scales individually they're not, right? So what we actually want is the emulator, where instead of noise, we put in high resolution initial conditions that you've generated, right? And then you get the emulated field out, and you can compare that directly to the true field, right? And statistically it should be the same, right? But the correlation coefficient of the Fourier modes should be, at least until the method breaks down, should be close to unity if you can make it, right? And then that means that you have actually produced an emulated field which is the same as the simulation, the true high resolution simulation. That's what you want. And if you can do that, that means you don't have to test all these statistics, right? Here you might say, okay, the power spectrum is okay, but does the super resolution do the bispectrum? Does it do the void probability function? Does it do what? And you have to test it each time just to show, right? But if it can do every single individual Fourier mode, then that means every single structure is the same, and therefore all statistics by construction are the same, right? And so this is kind of what it looks like. So here's a 100 megaparsec box up here, and zooming down into a 10 megaparsec box at the bottom, and you can see the super resolution here is where we had on small scales random noise, okay? And here's the target, the high resolution simulation. You can see that, you know, it's got these structures here, but they're not the same as here, but on large scales it kind of looks similar. And then here's the emulator, where we had this extra unit which moved these things around and made them more similar to the target, right, using the initial conditions. And you can see that it's not perfect, but it looks pretty good, right? It turns out that it actually works down to the scales of, you know, halos and subhalos as well, right? And you know, the speed is, at least for dark matter only, it's 10,000 times faster to do this than this, right? So that's obviously why we're doing it, right? If it's 10,000 times faster, then you can run it on, you know, a small GPU instead of a supercomputer, and you can do many of them, right? And so here's the correlation coefficient of the Fourier modes. Okay, I'm doing 1 minus that correlation coefficient squared, okay? And so you can see here's the generated super resolution. So on scales below k of 1, we've got this random noise came in. So although statistically the power spectrum is fine, the individual modes are not correlated. And here is the correlation coefficient. It's like a k of 10, which is pretty good. It's 5%, okay, between the emulator and the target high-res simulation. And you might say, okay, how good is that? Well, you can have a look at this. It's a bit old now, but this is a code comparison project for n-body codes, where we plot what is the difference in the power spectrum with all these different codes. I said it's a bit old, right? But you know, all these different codes, they're involving the same initial conditions, right? What power spectrum comes out? And you can see the residuals, and you can see that, you know, here's 5%. And you can see that the individual codes, right, these n-body codes, they can't even agree on the answer to within 5%, right? So the emulator is already doing just as well as different n-body codes, right? So if you say, I don't believe the AI, if you are reviewing my grant proposal, right, and you say, I don't believe the AI, well, that means you can't believe the codes either, right? That doesn't mean that I would get any funding from you, but okay, that's what I'm hoping, right? Anyway, so, okay. So that was for n-body stuff. I work on the Lyman-alpha forest a lot, and so I'd like to do that. It turns out it's perfect for this kind of thing because the Lyman-alpha forest doesn't care too much or hardly at all about star formation and difficult things, right? So we start off with the intergalactic medium, right? So it turns out that that's a good thing to start off with. And so you've got the simulation. Imagine you trace a sight line through it corresponding to a background quasar, and then you get a Lyman-alpha spectrum, right? You're mapping the intergalactic matter along the line of sight. The observable here is the flux is e to the minus tau, where tau is proportional to the neutral hydrogen density, right? This Gunn and Peterson, right? And so because it's a nonlinear transformation of the density field, to get this right, for example, if you want to know what is the mean flux, for example, you have to resolve the forest, right? You have to be able to actually resolve the gas pressure smoothing scale. It's about 100 kiloparsecs, right? So your simulation or your emulator has to be able to do the physics on scales of 100 kiloparsecs, okay? And luckily, the emulator does just fine, okay? So you might say, okay, why the Lyman-alpha forest? It turns out, I like the Lyman-alpha forest and I've been doing it for a long time. We've used it for cosmology for a long time, right? So at least since 1998. This is a paper, okay, I'm just doing this because, I want, I just want to show that it stood the test of time, right? I can show you papers with other cosmological probes where they got things completely wrong. Okay, and so Tomomi knows that I wrote a paper where I actually went back in time, right? And so this is a paper from 2002 that we wrote. This was our measurement of sigma 8 back then in 2002, right, from the Lyman-alpha forest, right? So sigma 8 is 0.82. Okay, it had a 10% error, but okay. And then here's from DESI last year, full shape modeling of clustering, and sigma 8 was 0.81, okay, with a much smaller error bar, right? And so back then, people told me that it's crazy in 2002. This is much too low. Everyone knows that sigma 8 back then was 1.2. But no, our result was 0.82. I'm like, okay, that's what we get. And okay, 20 years later, then, that's what the answer supposedly is, right? So, okay, so that's why I like the Lyman-alpha forest. So here, we add in for our training additional channels, right? We want dark matter and gas, right? And in the gas, we train on the density and the velocity like before, but also the temperature, right? Obviously, it cares about temperature. We also actually have star formation, and so we have although we don't care about the stars here, we have a binary quantity, which is the gas particle turned into a star or not, right? So we train on that too. Okay, and so we have a paper which came out, was actually accepted last week, so we're happy. And so what comes out is an emulated hydro simulation, right? And so here, as before, on large scales, you can see this is the emulator, and this is the high resolution simulation. This is the emulator, right? And they look kind of similar, but what about this Lyman-alpha spectra that we care about? Before I do that, you can plot the gas properties. It's not perfect, but it's okay. So this is the density, and this is the temperature, okay? And so it's a phase diagram, and you can see the Lyman-alpha forest is on this power law here, okay? Most of the gas, 99% of it at this redshift of 3, is on this power law here. So 99% is this weakly fluctuating medium. This is hot sort of X-ray emitting stuff, and here's galaxies forming, which we're not, we haven't gotten to the point where we can actually do that, or we haven't concentrated on it. Maybe we'll try next, right? So you can see that it doesn't really do the galaxies forming very well. But this piece, the Lyman-alpha forest that we care about, it does very well, right? So it can do, the physics of the Lyman-alpha forest. And so then we make spectra. Here's the emulator, right? Here's the high resolution hydro simulation. Here's the low resolution. This was the input to the emulator. Remember, the super resolution, we have an input initial conditions at high resolution and a low resolution, so you still have to run a simulation, but at low resolution. Okay, and so this is obviously the spectra are not good. Okay, it just doesn't look the same, but these two look pretty similar. And sorry, let me show you. Okay, so here, for example, is the density field along the line of sight. So there's one line, the emulator, and the other one, the true full gadget hydrodynamic simulation. Here's the temperature fields, right? This is the velocity, right? You can see, you know, that they're much better than we were expecting. You know, when I saw that, I didn't really believe it. Okay, and so here are the spectra from the emulator and the true simulation. I can't remember which is which, but anyway, so you know, it really, down to these scales of 100 kiloparsecs, it really works very well. You know, you can run volumes that people just used linear theory for, log normal models. Now we can do it with a precision that's as good as a hydro simulation, right? But you can see running the high resolution hydro simulation here on our local cluster, you know, it takes this many thousands of seconds. Running the emulator, including the low res hydro simulation and the neural network parts, 594 seconds, right? That's 10 minutes. Okay, so it's actually 450 times faster, right? So one of these, you know, is 450 times faster than the other. So you could make a simulation. That's what we want to do next. You could make a DESI mock survey, right? A simulation of 3 gigaparsecs on a side with a resolution of 100 kiloparsecs, right? Which is impossible with the full simulation. Okay, and the statistics, they also work fine. You know, this is the observational data for the power spectrum. You can see the observational data doesn't agree very well, but you know, the statistics work at least down to these scales to within, say, 3%, and then on these very small scales, it's not doing so good. But the data obviously doesn't agree on those scales anyway. That's a redshift 3. Okay, so that was, you know, I'll talk a little bit about the kind of things that we can use these simulations for in a second, right? But I'll go back, before I do that stuff, the science, I'll go back to the role of AI in astronomy, right? And so here, it's about doing the stuff that we don't like to do, right? Unless we're strange, okay? So for example, imagine that you can cast your mind back, if it's been a long time, you're a beginning grad student, okay? Like, you know, I remember my advisor was like, okay, you have to run a simulation, okay? Because it was a long time ago, it was like a simulation with like 1,000 particles, but okay. Now, it'll be something different, but okay. So I tell now to my students, please run a Gadget 4 simulation to do something, right? What do they need to do to run that simulation, right? They need to go on our local compute cluster, but they need to, okay, maybe I'll tell them use Gadget 4, maybe I'll say try and figure out what code to use, right? So they need to do things like that. They need to generate the initial conditions, which there are different ways of doing that. They need to install the libraries, and that might look like nothing, but it turns out that's the big rate determining step, installing the libraries that work, right? It just is very difficult. They need to install the code. Okay, then they need to find the initial conditions, spell it as well, I guess, and then they need to write the Slurm script because we're doing it on a cluster, right? Okay, and then they need to run the initial conditions generator and then figure out, okay, the simulation, how many snapshots, they want, box size, whatever, all sorts of things. Then, they need to write the Slurm script to run the simulation, which will often crash, right? Then they need to run it on the supercomputer. Then they need to deal with the output formats, which could be all sorts of different things. And then they need to run their analysis code, right? And so if you're an astronomer, an astrophysicist, none of this is what you did your PhD for, right? You didn't do a PhD in pip install stuff, right? Okay? So this boring stuff we don't want to have to do, right? And actually it does take, not continuous work, but it could take weeks to actually get it to work properly, right? Okay, so this is where our multi-agent system comes in. This is a sim agent. It was the first author is Xiaowen Zhang, and it was recently accepted to an AI conference. It's just a multi-agent system, right? So all it is multi-agents, these AI agents talking to each other, okay? And what does it do? Basically, it does stuff like it reads simulation papers, for example, or scientific papers, and then it figures out how to actually run a simulation, okay? It's restricted just to simulations. To run the simulation, execute it, it reads documentation, for example, for your local supercomputer facility. It reads the manuals for the code. It reads, things like that. Also the analysis. It does all those things. And there's a framework. There's many frameworks. We used AutoGen. We actually use relatively old now API for same one used for ChatGPT-4, right? OpenAI. And what kind of things can it do? It can produce, for example, a gadget parameter file, okay? And when it works, in these computer science journals, you have to test against other things, right? And so that one of the standard things to test is chain of thought and exchange of thought, and then our two-agent thing. Before I show you what those things are, you can see, for example, the number of type errors when you're trying to run a simulation. A type error, and I'll say what that is in a second, we're 20 times less than these other methods. What are these other methods? Chain of thought is a zero shot. It's basically like if you ask ChatGPT to do it. ChatGPT has all the information, for example, and because it doesn't talk to itself right, in the same way, it gets things wrong, right? It gets carried away, and exchange of thought is where we have two agents and they both have all the information. It turns out that that's also bad because each of them thinks they know everything and they don't actually help each other, right? But in our multi-agent system, each agent has its different thing. For example, it might have the simulation papers from the literature, and the other one might have the manual for Gadget 4 and how the supercomputer works, or something like that. And it turns out they do talk to each other, and that comes down, that means that the errors go way down because of that. So, it's a bit of robot psychology or something, but that's how it works. And we've compared this, but I don't have the results now, to mistakes that humans make, right? And this compares favorably with humans, very favorably, in fact. Okay, and so here's an example of a value error, right? What might a human do, or a bad agent? It might get the units wrong, and this has happened, to me and to my students, right? Imagine Gadget has kiloparsec units because it was originally designed for galaxy simulations, but now a lot of people use it for cosmology, obviously, right? And so you might get the units wrong. And so if you put in the initial conditions, you get the box size, instead of 100 megaparsecs, you get it of 100 kiloparsecs. You run it on the supercomputer, you waste all your time, and then you get, 100 kiloparsec box collapses at redshift 0 and looks like a big blob, right? So, this is the result of a type error which could be picked up by the multi-agent system, so you don't do that. Okay, and so you might say, okay, supposing I want to use it, how long would it take to run and analyze, say, a 512 cube simulation, right, with emulation, like I've talked about, which it can do. So, this kind of simulation, when I was a grad student, you couldn't think about doing it. Even now, you probably wouldn't do that on your laptop, right? It's a 512 cube simulation. If you run it, it takes about 2 minutes to run it and compute the power spectrum and visualize it, right? So that includes generating the initial conditions, running the full emulated simulation, and analyzing it, right? So if you wanted to use it to do simulation-based inference or whatever, you could do that, right? So that's how it works. Okay, so I'm going to talk a bit about some science now, and I apologize, I'm going kind of fast. I always have too many slides, but okay. So I like the Lyman-alpha forest, intergalactic medium, so I'll talk about two papers, which is based on some recently published work, lensing of the forest and quasar proximity effect. Both of these things are things where the hydrodynamic emulator could be very useful. They haven't been used yet for these, right? But I'm starting a project where we're going to use them for both, because they're the kind of things where you need a giant volume, right? A high resolution. Okay, so what about Lyman-alpha forest lensing? So first of all, let's talk about galaxy weak lensing, right? So what problems can you have with galaxy weak lensing, right? So, you probably know that there are issues about whether the amplitude from lensing is low, right? Whether that's due to baryonic feedback or various other things. But, people are not 100% certain because lensing is very difficult. You have to measure the shapes of galaxies and how they're distorted, right? Real galaxies are ugly, so you're particularly for ground-based imaging, you have to deal with lots of difficult image analysis questions. Also, you need to know the redshift of the background sources, and that's also difficult. So they're very faint, you can't get spectroscopic redshifts, and so that's obviously a big problem. There could be catastrophic outliers in the photometric redshift determination, and all sorts of things, right? It's difficult to do. So it turns out that in principle, you can get around this using other things that you lens, right? Obviously, you can lens anything, okay, as long as it's, there's some mass to lens in front of it, okay? And so that's why CMB lensing is so powerful. The lensing kernel for the CMB peaks at redshift 2.5, and so that's most useful for that. Obviously, it's a great probe. It turns out that, imagine you took the Lyman-alpha forest at redshifts of, say, 2 or 3. The lensing kernel would peak at redshift of 1, right? And so that's a different regime. It's actually higher than for the galaxies, but lower than here. It's actually right about when, maybe dark energy might be evolving, for example, right? So it might be good to look at it. And so the idea was to try and lens the forest, right? So how would that work? Well, obviously, if you've got a lens in front of your quasars, the quasars will be deflected, right, compared to the observer, but also all the spectra, because they're attached to each quasar, right? So when you look at them, you figure out their angular position, and that will move. All the pixels in the forest will move because the quasar has moved, right? So effectively, all the clustering from these things is being moved around by the lensing effect, right? And it's easier to see if you look for like an individual pixel. So imagine here we've got the lens. Here's the quasar, right? This is where the quasar actually, this is where it appears to be. No, sorry, this is where it appears to be, sorry. Okay, and this is where it actually is, right? And you've got the path, it's being lensed like this, okay? And so you think that it's here. Now imagine that you correlate this with another pixel in another spectrum, right? And so the actual correlation basically will be this correlation between these two pixels, so kind of weakly correlated, but you'll think that the correlation is this correlation. They're closer, right? And so it's more strongly correlated, right? And so this is, just what lensing does of the CMB, for example. And so you can use this correlations between these pixels. You can invert that using a quadratic estimator and then figure out what the lens is doing, right? And so the problem is that unlike the CMB, where you can put your quadratic estimator onto a nice grid, okay, and do it in Fourier space, here the sight lines of the forest is just the quasars, which are essentially randomly distributed, and so they're discrete, and the estimator is very complicated to figure out, right? But luckily, Ben Metcalf was working on this, and he basically figured out how to do that. And so, we've started making mock DESI surveys, okay, where we want to figure out the potential of the foreground mass, right? And so here's the potential from mock galaxies. It turns out we want to cross-correlate the galaxy positions with the lensing signal to actually detect it. Turns out that it doesn't work very well, unfortunately. We made 20 mock DESI surveys, and this is the amplitude with respect to the true amplitude. And you can see that it can detect the lensing signal from the forest only with a signal to noise of about 4 for the whole of DESI, which is kind of disappointing. And you might say, but with the CMB, you can do it much better. Why is that? The CMB has these wiggles, right? And so when you see them being shifted, it makes it very easy to pin down the lensing deflection angle. Whereas here, we're in the regime where the Lyman-alpha forest is almost scale invariant, and it just really is very difficult to see. The clustering doesn't change very much when it's shifted. Also, the DESI Lyman-alpha forest is very noisy, right? And so that also affects things. But in the future, there are other surveys that have a much higher density than DESI, and you might if you wanted to get a signal to noise detection of 10, how many spectra do you need? And a few tens of thousands of spectra with a space density is enough. And so there are other surveys that are better for this than DESI, right? And so it should happen, and it should give us an estimate of the matter density that is not biased by galaxy weak lensing issues, right, and is at higher redshift. So we'll see about that. Okay, so now I'll do the last piece that I was going to talk about, looking at the Lyman-alpha forest, is the quasar proximity effect. And so this is a very esoteric subject, which hardly any people work on, but I always liked it. I always thought it was fun. So the paper that was written about this, the first one, was 40 years ago, almost now, by this guy, Batchlick in Princeton at the time, right? This is a picture of him now. That's not how he looked 40 years ago, but that's how he looks now. So he's a happy guy. He's still working. I never met him, but anyway, he wrote this great paper where he said, okay, imagine that you've got quasars in the intergalactic medium
their own radiation is going to photoionize the intergalactic medium around them. And so there should be some effect in Lyman-alpha forest spectra where you have less neutral hydrogen close to a bright quasar than a faint one, right? So if you look at the spectra, imagine this is the position of the quasar here, and this is moving away from the quasar. You can see that the flux here, right, if you have a bright quasar, you're close to the continuum, so there's not much absorption. You've got lots of ionized hydrogen. And then when you move further away, you get back to the regular forest, there's lots of neutral hydrogen out here, which is here, right? And if you've got a fainter quasar, that happens but over a smaller radius, right? You can see the radius here, and then you've got the regular thing, right? So this effect close to the quasar is called the proximity effect, right? And it's an interaction between the quasar radiation and the intergalactic medium, right? It's kind of a fun interaction because it can stretch over distances of 10 or 20 or 30 megaparsecs, right? It's a long distance. You're probably used to, feedback winds and things. They don't go that far, right? That's why it's kind of a nice thing, okay? And so it turns out that people have not looked at this very much, right? The largest samples in data, for example, from 2017, is 30 quasars, right? Nobody has done this for large surveys, even BOSS or eBOSS, and certainly not DESI, right? So DESI, instead of 30, has 800,000 quasars, right? Imagine you could go from, 30 to a million, right? That's a big difference, right? 5 orders of magnitude in data, so you should be able to do something with that, right? And so that was the idea that we sort of thought about. How could we analyze huge samples of data in a way that's more sort of modern than what was done 40 years ago? And so what we hit on was we would just use a halo model, right, which is what people do. It turns out it's well suited to this. What we want to do is we want to figure out eventually, right, what is the Lyman-alpha forest flux as a function of distance from the quasar? And for the halo model, we'll start off with the density field, right? And so, those of you who are familiar with the halo model of clustering, you have the one halo term, so that's material in the halo itself, which, we use the Navarro-Frank-White profile. It doesn't really matter too much, it's not sensitive to that. Then you add in the two halo terms, so how are those halos clustered? And in this case, it's not really two halo, it's actually the correlation between the halo and the density field itself, but it's the same form, it's just a linear curve, right? So we use the linear CDM correlation function, and then you add them together and you get this this profile, right, of density. And then because we're looking at something which is a nonlinear transformation of the density field, which we need to get right, turns out that you can't just have a single point, because if we converted that mean value into the mean value of the Lyman-alpha forest flux, that wouldn't work, because it's a nonlinear transformation between density and flux. So we have to keep inside each pixel a whole PDF. We just use a log normal PDF with a certain width, which it's not very sensitive to. So you add that inside each pixel, you convert that into a Lyman-alpha forest optical depth using a parallel relationship between density and the neutral hydrogen density, which again we get from simulations that it works well, and I showed you before as well. And then the next thing we do, because it's around quasars, we need to put in a radiation field, right? And so we use a simple radiation field for now, which is just the inverse square law, right? 1 over r squared. And so here, J is the radiation intensity as a function of distance, and it's just 1 over r squared, but it includes two things. It has 1 over r squared from the quasar, and then it has a uniform radiation background, which is this thing out here. That's the radiation from all the other quasars in the universe and maybe galaxies. Because there's many of them, it's pretty close to uniform, and so we just model it in terms of two components, the quasar plus a uniform background, right? Turns out that this uniform background is actually what we're interested in most in measuring, and that's what people have used this to measure before, right? Okay, so, and then once you've done that, you just multiply, or you divide the optical depth, the neutral hydrogen optical depth, by the ionizing background intensity, and then you get the optical depth, which goes down close to the quasar, right? There's not much neutral hydrogen because of the radiation, and then back here it recovers. Okay, and so there are other effects that we need to put in, thermal broadening, because we're observing in redshift space, and so we put in the temperature of the gas. There's also infall velocity around the quasar. We have gas falling in, and so we put a spherical infall model which shifts the curve a bit, not too much. And so, by having a halo model, we account for the fact that halos live in dense regions, right? That's what previous analysis had trouble doing. You have to make the assumption there's actually more neutral hydrogen around the quasar because it's in a dense region. How do you quantify that? You can use the halo model, right, to do that. Okay, and so then what comes out is just the flux as a function of distance from the quasar, and here we're going up towards the continuum, and then here's absorption, and this is the sign of the quasar radiation, right? And so, this is just what the model looks like. It's not very interesting, but one thing that we do have as a parameter in here is we parameterize the effect of the quasar's radiation by the radius at which the quasar radiation is equal to the background field. So imagine the quasar's radiation, it goes down like 1 over r squared. At some point it becomes equal to the background field. At that point there's equal, each neutral hydrogen atom sees equal radiation from the quasar and the background. And so if you care about the background, then you can use that because here the equation for this radius, right, just comes from the 1 over r squared law, right? That's why there's a square root here. You've got the quasar luminosity, which is something that you can measure. If you know the quasar redshift and you've got its spectrum, you measure how many photons are coming out of it per second. Okay, and then here the unknown quantity is the intergalactic radiation intensity. Okay, so you can invert this. If you can measure this from the observed spectrum, right? If you can measure that, then you can, and you know this, then you can figure out what this is, right? And so that's what people have done effectively before when they wanted to know how does this vary with redshift. Okay, but now we have a lot more data, so we can do other things. Now, to show that it works, we need a simulation, right? And so we tried it on simulated quasars. So we used our simulation I talked about before, the ASTRID simulation, right? Earlier this summer, it reached redshift 0. Here's just some dual AGN, for example, in ASTRID. The data is public, if you want to download. We have 10, 12 petabytes of raw data, but you don't have to download that. But there's the halo catalogs and all sorts of other things on the star particles and other stuff in halos that you can download. And because it's 250 megaparsecs on the side, there are a few quasars in there that we can use. There's a lot of black holes in there. So actually, I wanted to show you, okay, for example, one of the things, unfortunately, I won't have time to talk about, is that you can look for little red dots to see if there are some, and there are some in ASTRID. You can measure you can make spectra of, we have quasars, we have galaxies, we have dust and other things, and you can see, it turns out that there's not too many, but there's a few. There's less than seen observationally, but anyway, so we have a paper about that, which you can look at if you're interested. Here's a plot that, I made that was deemed to be too disturbing to go into our simulation paper about the simulation. It actually looks nicer on my screen than, I don't know, the projector doesn't work, but I don't know if you can see, it's this sort of weird red thing. And they told me that it was just too disturbing and they didn't like it. So I wanted to show it now in every talk because, I want to disturb you. What are these things? They're the tracks of black holes in a slice in the simulation. And so all I did is I colored them as a function of their mass, right? And here, this is 10 to the 9 when they're this sort of yellow color. And, these ones are 10 to the 6. And as they move through the simulation, they accrete material. And there are millions of them in the simulation, right? And they all have these tracks. And unfortunately, the projector it doesn't work very well. But anyway, I can show you on my screen, and it's kind of nice. But anyway, so just to remind you, there's many black holes, so there's definitely quasars in there, and so we've tried testing out the halo model on the quasars in the ASTRID simulation, and so here are some of the theory curves compared to the average from the simulation for a few quasars. Not too many because it's not such a big volume. There might be, say, 10 or so of each luminosity in this curve, and that's why they're wiggling a bit. But it works pretty well when this equality radius, right, between the quasar radiation and the UV background is large, that means that the quasar is very bright. Okay, so it can equal the UV background even at a great distance. If the quasar is pretty faint or has no proximity effect, then you get not much effect in the mean spectrum, right? Okay, so what you can do is you can actually fit that halo model to individual quasars, right? They're obviously much noisier than the averages because the Lyman-alpha forest itself acts as noise. But here they're ordered in terms of, I guess, the fit value of this equality radius. So this must have been a super bright quasar, and these ones down here much less so, right? And although on an individual basis, it's noisy, it still can be done, right? And you can compare, for example, what is the true radius at which the quasar radiation equals the UV background to the one that we fit from the halo model. And you can see that there's this correlation, and you can get the radiation intensity. It depends on how bright it is. The brighter ones are better, obviously, because the quasar has more of an effect. But even the faint ones, the RMS is maybe 20%, sorry, it's 50%, and up here it's more like 20%. So each individual quasar, you can measure what is the radiation intensity that quasar sees from the rest of the universe, right, at that position of that quasar. And so if you have 1 million of them, right, in DESI, say, you can use that to try and map out the radiation field in the universe in 3 dimensions, right? And so that's what we did here in a 2 gigaparsec simulation. This was done with just a dark matter simulation, but it's something I would like to do with the emulated hydro simulation. And you can see, although it's not perfect, this is the true radiation field that went in. The true radiation field I just get by summing the radiation from all the sources in there, all the quasars in the volume, using the 1 over r squared law. And you can see these fluctuations. They're of order, maybe 5%, okay, in the UV background. And then here's what happens when we fit the proximity effect to all those quasars, and we get values at the positions of all the quasars, values of the UV background field. And so this is not a density field, right? It's a radiation field, right? And in principle, it could be something interesting for cosmology, maybe, right? For example, here's the power spectrum. This is the power spectrum of the density field. This is the linear density field, but okay. And then here is the power spectrum of the true radiation field here. And this is the one that we fitted with a proximity effect with our halo model. It's this thing with error bars, right? And it works okay. All right, it turns out that's actually the simulation is a bit smaller than the DESI volume, so maybe DESI could do better. And you can see that on very large scales, there's actually more power in the radiation field large-scale structure than in the density field, right, by a factor of, a few. Okay, so it's kind of interesting. It could be a way of testing cosmology on very large scales or something, right? Who knows? I mean, it'd be nice to measure it and then see, okay? And here was just the correlation coefficient of the true fields with the fitted field, just to show that there is some correlation, even though the visual maps weren't great. And if we had a randomized field, there isn't any, right? Just to show that it does work. Correlation coefficient is of order, 0.5, which is okay. Okay, and so, we started doing this with DESI. Here's some fits in 3 luminosity bins of quasars, the proximity effect and different models. We've just started doing this, my student Patrick Shaw, but it's kind of like the simulation results, the average one, but we'll do it for individual quasars and hopefully make that map for the DESI data, right? Okay, so I'm almost finished. I'll just go back one final point about AI, and this is related to yesterday's seminar that some of you probably were in this room to hear about, okay? And it's to do with the amount of energy that we use and our imprint on the environment. Okay, so there was this nice study by Stevens et al. This is 5 years ago now, but it was done for Australian astronomers, right? What is the average tons of CO2 per year per person, right? Do astronomers actually use up? And you can see that flights, observatories, and offices are a small fraction of supercomputing, okay? And this was for 700 Australian researchers, right? They use 400 million core hours. So in our group, we have 10 people and we use 500 million for one simulation, Astrid, right? So we're much worse than this, okay? So anything you see, I'm much worse, and maybe some of you guys are much worse too, right? What is this? I don't really know what this means, this number, right? So I turned it into something that, Americans can understand. It's the same as every person in America who is an astronomer driving 3 of these trucks, right? F-150 pickup trucks. So I drive a small Honda, right? I think, oh, okay, I'm not hurting the environment, but really because of the simulation, this is what, an average astronomer is doing. You're driving these things, okay? Now in America where I live, there are people who do this because they hate the environment. They buy them on purpose. They do this thing called rolling coal, where they have them modified so they blow out black clouds of gas and whatever. But okay, this is, we're just as bad, right? And I wanted to translate it into a Taiwanese version, right? So if you go out and see, I see many of these CMC pickups, right? China Motor Corporation, I guess. And it's the equivalent of 37 of these, right? So if you guys are out there, and you count 37 of these going by, that's what you're doing, right? You're the equivalent of these, okay? Okay, so that's bad, right? And this is about supercomputing, but AI is probably going to be even worse, right? And so I want to be a little bit positive, and we can improve what we do. And I think the talk yesterday was a bit about this, right? So it turns out that, this guy, world Go champion, his brain power consumption 20 watts, right? And he was beating Google until, a couple of years ago, right? AlphaGo. AlphaGo runs with a megawatt, right? So, 10,000, 50,000 times more energy, right? So it is possible to do better. Maybe we should convert all our AI and astronomy to, some new weird artificial brain or something. But anyway, and there's some way, we can, in principle, do better in the future. Okay, so that was the last point I wanted to make. So here's my conclusions, right? So the super resolution emulator, we've done it for intergalactic gas. We've done it for n-body simulations. We want to go on smaller scales. We want to be able to emulate star formation, which obviously is difficult, right? And black holes. And we have ideas for how to do that. And then, we could do a full simulation, but very quickly, right? Doing all this full physics. With Lyman-alpha forest resolution, we're starting now also to do 10 to the 14 particle simulations, emulated simulations, right? That turns out is organizationally difficult because, we don't have, 100 petabytes for each snapshot that we can store, right? So we have to make the spectra as the simulation is super resolved, right? And then output the spectra in pieces and so on, right? It's just an organization thing, but it's tricky to do. For the Lyman-alpha forest lensing, hopefully DESI will be able to detect it, but in the future, things like PFS will do much better. And then hopefully DESI will map out this intergalactic radiation field, which might have some surprises in it. It will tell us about the sources of radiation, maybe about cosmology, who knows? And then in terms of AI, right, we really want to make sure that if you're involved in AI, don't try to replace humans, right? Don't try to write an AI that will, write papers and, log into your bank account and spend your money or whatever, right? Don't do that. Just write some AI that will help you do your job, do the boring piece, and help us do our jobs, right? Because we want to do the fun piece of astronomy, right? So that's what I'm hoping. Okay, that's it for now.
Two-ish questions. So
sure.
The first one is the forest lensing. I guess what you showed is some kind of a shear type of lensing. Is there anything that could be potentially measured for magnification?
Right. We're looking at quasars, right? So you can obviously measure the magnification of the quasars themselves. Yeah. And so that's what people. That's what people have done, right? In terms of the forest, right? Because if you magnify the quasars, it doesn't change the forest. It would be nice to, maybe you could cross-correlate the lensing from magnification of the quasars with the forest lensing, maybe, right? Because it's the same foreground lens.
It's the same fraction of absorption.
Yeah. So, sure, that's why it doesn't change the, So if you cross-correlated both signals, that would help you, I think, yeah.
And then the second question is about proximity effect. I saw some of your plots for very small R equivalent,
Yeah.
actually does the kind of, you see even stronger absorption, so that sounds like a negative
Okay.
proximity
Like-
effect.
On very, like, where, which, like, one of the,
You have
oh, right, yeah, this
7,
this one?
which is the mean. and
Yeah,
then
okay,
You have
yeah.
something that's absorbing even stronger than the mean.
This one here.
Yeah.
Yeah, okay, sure. So this was where I didn't put the quasar radiation in. So this is, quasars live in dense regions, right? And if you discounted their effective ionizing radiation, right, then this is what you would see, right? If they stop shining, you would see that there's more neutral hydrogen close to a quasar, right? So that's why. Yeah, so this turns out that this absorption here tells you something about the mass of the quasar halo, for example, because more massive halos live in denser environments. So you can actually use this to constrain, the quasar halo mass. So yeah. Yeah, okay.
Yeah, I'm interested in the AI super solution part.
Okay.
Yeah, so I'm wondering how do we assess the applicability of the emulator, and in which situation do we are we required to retrain the model, for example?
Right. Sure.
Different cosmology, for example.
Yeah, exactly right. Okay, sure. So this is the question, right? So any question about AI is about, what do we do for training, right? I don't know why I'm going through this, but anyway, so yeah, we obviously need to have a data set when we train that actually represents, what we're trying to emulate, and we've used an architecture called a style GAN, where we give it information about the cosmology, for example, or the redshift, which is an additional parameter, additional input. And then when we train, we also tell it what that is, right? But you have to somehow be able to train on enough data somehow, right, to be able to interpolate between cosmologies, say. And it's not clear how to do that. And that's something that people have not done enough of, right? So we're actually trying now with using the Quixote simulations, which are a big set of many different parameters, to just see how well we can do that. It turns out that with the emulator, it's actually not too bad, because the emulator actually emulates the structure, right, precisely, the individual structure, right? So if you have a cosmology where the initial power spectrum is different, it just means the structures end up looking different, but it can still get them one-to-one, right? It just thinks that there were weird initial conditions, right? But it doesn't, but it has the initial conditions, so it doesn't matter, so it knows them, right? It's where the problem is when you have different growth rate and things like that due to evolving dark energy and whatever, and then it might have trouble moving things, right? And so all of these things have to be done with experiments, right? Numerical experiments, unfortunately. And that's the problem with AI, is because it's not something you can write down equations for what it's doing, you just have to treat it as if it was, some sort of experiment that you're trying. So yeah, and that's, we don't know how many training examples you need to really get it to work, right? Maybe we're actually using too many, or who knows, right? So yeah, it's just a big issue, and I think we all have to face that. Yeah.
Yeah, I just want to comment about this, using the image to see this high resolution structure, which you cannot see in the low resolution large box ROM.
Yeah.
Because when we talk about resolution, we are thinking about, we want to have high resolution, we want to resolve the small scale physics.
Yeah.
So the key thing is about the physics is not just look like, oh, this is a galaxy, this is a star, whatever.
Yeah.
So the high resolution will involve the small scale physics, which involves a complicated nonlinear process.
Yep.
So it's not just the outcome of the result. So I think was when you say you have a super high resolution emulator, you can suddenly generate very high resolution results.
Yeah.
So I really question about this part of the fidelity of the result, because how can we trust this result?
Right, sure. Okay, when you have a simulation, right? So you're running it with approximations. You're running finite time steps, all sorts of things, right? It's not actually doing the real, analog physics, for example, right? And so you have to trust it in some way too. So here we have a similar situation, right? You could, and we have done, you can run the emulator and use it to produce movies, for example, of forming structure, halo merger trees, because you can output at any point that you want, right? You can produce, the format of the emulator is the same as the simulation, right? It has particles, they each have an internal energy, they have a, metallicity, whatever you want, right? And so in the end, right, you say, okay, but it didn't really do the physics, right? But again, that's the puzzle, right? It somehow does do the physics because it's learned the physics from the training set. You could, of course, add in some physics knowledge, right? And people do that a lot. We haven't done too much of that, but you could add in conservation laws and other things, right? But given that, supposing, if your emulated simulation, imagine it worked perfectly, every particle was exactly the same, position, velocity, temperature, every property, right? Then the high res. Then you'd be like, okay, well, it's doing the physics that I put into the true simulation, and it's just doing that in its own fast way. But if I want to learn, the physics, I have to remember what I put into this, right? And I think you have to look at it that way. Right now, it's not as good as that, but it's not bad, right? It can do, it can do some, physical properties. For example, I showed you the temperature density relation, for example, and things like that. So it's not just a picture, right? It is the three-dimensional distribution of particle elements and so on, right? But yeah, but you can always say, it's not the real thing, so yeah, sure, I agree, right? So.
Any other questions? If not, let's thank him again.
All right, thanks.